It has been a while since I've done a video. I've been really busy working on a top secret project that not even my Patreons know about yet. So I have been very, very busy, but let's do a video today. Welcome back, everyone. I'm Robin from This Blog's Neat, and I am so proud of future Robin for coming up with a creative enough title to get you to click on a video about chemical analysis of distilled spirits, because we're going to get real nerdy today. We're going to talk about the chemical analysis of my 3 rums, compare them, and then discuss how those results are actually obtained. So I'm going to teach you guys how to look at and read a chromatogram and explain how those results are obtained. So let's dive right in. So as you know, I have 3 different rums, and I have gotten the chemical analysis done on all 3 of those rums. The idea being that you are able to taste the differences between switching up variables in the production process, but also you're able to see the impacts that changing these specific variables in the production process actually has on the chemical composition of those rums. So we're gonna start with the results from my 3 different rums. Now, just as a refresher, my 3 different rums are baseline, variable, dunderclap, and variable tailspin. Baseline is my baseline rum. It's molasses-based, molasses water distiller's yeast that is double pot distilled and bottled completely unaged. Variable dunderclap has dunder added into the fermentation. Everything else is kept as consistent as possible to baseline. And then variable tailspin has dunder added into the fermentation, as well as tails added into the distillation and dunder added into the distillation. So there's extra dunder, extra tails being added in during the distillation part of the process here. So those are the differences between my 3 rums. So keep that in mind. Now, I sent all 3 of these rums off to White Labs for chemical analysis, and they only test 10 analytes, and we're going to talk about those. They test for alcohols. The predominant alcohols besides ethanol that are present in the rum are amyl alcohols, which actually is comprised of a whole bunch of fusel alcohols or higher alcohols than ethanol. And they tend to taste alcoholic and can be a little fruity, supposedly. Another alcohol that they test for is isobutanol, which is another fusel alcohol, and that can be sweet and musty. They also test for 1-propanol, another fusel alcohol that is alcohol-like. And the final alcohol that they test for is methanol, which I know you have heard about. It's the smallest alcohol. It's smaller than ethanol, and it's supposedly sweet and pungent. And as I'm sure you know, if you drink enough of it, you can go blind or even die. And I've got a video about that if you want to learn more about methanol. White Labs also tests for esters, which I am certain that you have heard of before, heard me at least talk about them before. Esters tend to be fruity and floral. And the most predominant ester, ethyl acetate, is one of the analytes that White Labs tests for. It tends to be sweet and fruity. They also test for isoamyl acetate, that's banana-like. They test for ethyl butyrate, which is fruity and pineapple-y, and isobutyl acetate, which is fruity and floral, another ester. And then they test for 2 other analytes. We have acetaldehyde, which is an aldehyde that is pungent, ethereal, green apple-like, and acetone, which is a ketone that is like acetone, right? Nail polish remover. So just for fun, let's take a look at the actual chemical structure that makes an alcohol, an ester, etc. An alcohol is a hydrocarbon chain that has an OH attached to it, a hydroxyl group attached to it. So if we now rearrange the structure a little bit, the alcohol structure a little bit, the functional group at the end, and double bond that oxygen now to the carbon group, we get an aldehyde. So for an aldehyde, we have a carbonyl group that's bonded to a hydrogen. Now, if we remove that hydrogen and instead put a hydrocarbon group, we now have a ketone. And if we now stick another oxygen in front of that additional hydrocarbon group, that gives us an ester. Hopefully I didn't lose you guys there. But let's move on to the trends that I saw between baseline, dunderclap, and tailspin. How's it going, guys? This is future Robin here. I hope you're enjoying the video so far. I am interrupting because as I was finishing up the edits on this video, I received some results from White Labs from my most recent batch of baseline, which I haven't announced that I made yet because it's not bottled yet because I was waiting on the chemical analysis from White Labs. But that means I have additional data to look at, additional chemical analysis data to look at, and it kind of changes my original conclusions on these very preliminary results. So let's talk about those instead versus the results and conclusions I had prior to getting these results. As you can see in the chart, I have included the concentrations of 10 different analytes that were measured for baseline, both baseline batches, 1.24 and 1.25, as well as both variable batches, dunderclap and tailspin. I've also included the average of the baseline results to just kind of help me to see if we could maybe make some conclusions between baseline, dunderclap, and tailspin. Now, if you're one of my Patreons, you know that when I made this batch of baseline, I kept it as consistent from the last batch of baseline as possible. And we have already discussed these results and the potential differences that you see. But right off the bat, when you're looking at these results, you can see that the total congener concentration for this latest batch of baseline, 1.25, is higher than the congener concentration for any other batch I've done, including the last batch of baseline and both variable batches. And also, the ester concentration from this batch of baseline is the highest of the 4 batches that I've done, including both dunderclap and tailspin. So, based on all of these results and the trends that I'm seeing, it looks like adding dunder to the fermentation, as well as adding dunder and tails to the distillation, increases both methanol and 1-propanol concentrations. I'm confident in those results. It also looks like isoamyl acetate concentration decreases with the addition of dunder in the fermentation and dunder and tails in the distillation. It seems that that has a downward trend. And it would seem that adding dunder to the fermentation may actually decrease the production of amyl alcohols and isobutanol. However, it looks like adding tails into the distillation actually increases their concentration, the concentration of amyl alcohols and isobutanol. Now, prior to getting these results from this batch of baseline, I concluded that adding dunder to the fermentation and adding dunder and tails into the distillation increased ethyl acetate concentration. That seemed pretty clear to me. However, because the concentration of ethyl acetate for baseline 1.25 is higher than all the other batches, I can't make that conclusion any longer. So that leads me to believe that ethyl acetate production is actually impacted by other factors, probably during the fermentation. For instance, nutrient timing. When you're adding nutrients to the fermentation, I think this may have a little bit of an influence. And the reason I think that is because with this batch of baseline, I ended up adding only a very little bit at the beginning of the fermentation, like day 1, and then adding nutrients at day 5. Now, normally I add my nutrients at day 2, and I've done that consistently, but for timing reasons and scheduling reasons, I was not able to do that for this batch of baseline. There might also be something with the fermentation temperature. For instance, this batch of baseline had a much lower starting temperature than the previous batch of baseline. I think this might have something to do with it. However, higher temperatures, higher fermentation temperatures are usually associated with higher concentrations of ethyl acetate. So it might be a combination of things. Anyways, these preliminary results confirm that I need to do more batches of these rums so that I now have an average of the concentrations of the various analytes tested by White Labs. And that will allow me to accurately observe trends based on the different variables that are changed during the production process. Okay, back to past me. So as I said, I feel like these results are preliminary results, right? And I want to do more batches of the same rum to see how the congener concentration varies between batch to batch. Okay, so now let's talk about how these results are actually measured. And I find this really exciting and really interesting because I have firsthand experience with doing a bunch of chemical analysis, and I wish I had the tools at my disposal to do the chemical analysis myself, but hopefully future Robin will. In order to do chemical analysis of a mixture, right? Your spirit is a mixture of all these different chemical compounds. And in order to do chemical analysis, you need to separate out those chemical compounds and then detect them. So it's like we have a giant bowl of M&Ms, right? And first you need to sort all the M&Ms by color. And then you can count how much of each M&M you have, right? So this is kind of what we're doing with our spirits. In chemical analysis, this separation is called chromatography. And for distilled spirits or gases, you are using gas chromatography to do this separation. Now, a gas chromatograph is essentially an oven that has inside it this thing called a column, which looks like a really, really, really long, teeny, 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 tiny straw. Generally speaking, the smaller, more volatile compounds will move their way through this column, through this straw, a whole lot faster, whereas the larger compounds are going to take a little bit longer and move through it slower. Now, there are different types of columns and different lengths that are all going to separate your mixture differently. So an analytical chemist is deciding what column they're going to use and how they're going to program this oven to control the separation of those compounds depending on what your mixture is made of. Once they have been separated, the next thing that comes is the detection. And there are also various detectors that you can use depending on what your goals are. In the past, I've used a number of GCs that are paired with different detectors. But what I've used for chemical analysis of distilled spirits in my lab when I worked at Lost Spirits was GCMS, gas chromatography mass spectrometry. Now, White Labs, they use GCFID, gas chromatography flame ionization detector. And the reason they're using that is because that is better for actually quantifying the amount of each analyte you have in your mixture. I use GCMS because the mass spec is better for identifying those different compounds. There's also GCO, gas chromatography olfactometry, and I am dying to use one of those. It's kind of like this little gas mask that's coming out of the GC, and it requires a human to just stand there and sniff. How cool is that? Anyways, the whole point of me mentioning that there are different detectors attached to GCs is because depending on a whole number of things, your results are going to look different. And it's up to the analytical chemist to decide what they're going to use in their GC, what detectors they're going to use, what columns they're going to use, what kind of method they're going to use. And that's all based on what they want to see and what they want to detect and what they want to measure. So let me show you an actual chromatogram. So this is the print up version that comes from the GC FID at White Labs. And this is of baseline. So you can see it like kind of looks like an EKG or maybe one of those seismograms or a lie detector test, right? There are these little peaks that show up, and the x-axis is the time and the y-axis is the abundance, and each peak is a different compound. So you can see that there are peaks for methanol, acetaldehyde, ethanol, acetone, propanol, etc., all the way up to ethyl octanoate. This is what the GCFID is capable of measuring and detecting. This is also the order that they get separated by the GC. For example, it looks like it takes ethanol 1.7 minutes from when the sample was injected to get to the detector, and 4.96 minutes for the amyl alcohols to get to the detector, and so on and so forth. Generally, the larger the peak, the greater the concentration of that compound. So obviously you can see here that ethanol is the most abundant, which makes sense because there's a lot of ethanol in here, 75%. And the analytical chemist will tune their GC so that they're able to get great separation between these peaks, great resolution of these peaks, and also so they can calibrate to get an accurate measurement of the quantity of each of these compounds in the mixture. Now, this chromatogram does not show every single chemical compound that is in baseline. No chromatogram will, but as I mentioned, you can modify the GC and modify the detector so that you are able to see more things depending on what you're looking for. For example, here is a chromatogram of a lightly aged rum analyzed using a GCMS. Still looks like a lie detector, and the axes are the same, right? Time is the x-axis and abundance is the y-axis. But you can see that there's some obvious differences between the GCFID chromatogram and the GCMS chromatogram. Like there's more peaks in the chromatogram from the GCMS. So here I've highlighted the analytes that were identified by White Labs, the same analytes. And then here are some of the other peaks that are present. So there's more going on in this rum than what White Labs GCFID is able to detect. Now, this is partially because this is a slightly aged rum versus baseline, which is completely unaged, but it's also just because we've zoomed out and the GCMS is equipped to find different chemical compounds, separate and detect different chemical compounds than the GCFID at White Labs in particular. So if White Labs wanted to zoom out and be able to detect and measure compounds such as 4-hydroxy-2-methoxy-cinnamaldehyde, they would choose a different column that would allow them to do that. Now, keep in mind, seeing more is not always better. There are a number of benefits of just selecting specific compounds that you're looking for. Seeing more, one of the downfalls is that the peaks can overlap one another. Like you can see right here, there's one big peak that is overlapping this little teeny tiny peak right here. This is called co-eluting, and it makes quantifying those compounds very, very challenging. So again, in White Labs' case, they have chosen 10 analytes that they want to be able to measure and detect very accurately. So that is how they have tuned their instrument. So why would I show you all of this stuff? Why would we talk about this? Let's bring it back to the why, besides just the fact that I think chemical analysis and chemical analysis of spirits is really cool and really fun and interesting for me. I wanted to show you this to say we tend to focus on specific chemical compounds of a spirit, right? In rum, we talk all the time about esters. There is so much more going on than just esters in your rum. And all of this is playing a role in what you're smelling and tasting. In whiskey, I feel like you focus so much on phenols, right? In peaty whiskeys, we focus on phenols, and it's much more going on than just the phenols or what types of phenols are there. Every single part of the process is going to impact the chemical composition of your rum, and that means it's going to impact the flavor, the texture, the aromas. Do you need to get the chemical analysis done on your rum in order to understand more about it? No, you definitely don't. We are built with little compact mini GCMSs right in our olfactory epithelium right up here. Anyway, I hope you thought this video was interesting and enjoyed it. And if you want more videos like this, or you have any questions at all, if I've brushed over something way too fast and it was confusing, please let me know in the comments below. If you would like to support the channel beyond just watching more of my videos and liking, subscribing, all that stuff, you can join us over on Patreon. I've got a link in the description below. And thank you so much to my Patreons for all your support. I think we've got a really fun community over there on Patreon, and I try to share as much as I can of behind the scenes stuff with my Patreons, and they always get to know the secrets of what I'm working on before they actually come out. So this secret project that I've been working on, they will hear about it very soon. Anyways, thanks for watching.